Hello and welcome to this lecture on introducing OpenGL. So we are going to start talking about the primary API that we are going to use to program computer graphics in the course. So what is OpenGL? OpenGL is an acronym for the Open Graphics Library. It is an API that is used to specify geometric objects in 2D and 3D and to control how they are drawn into the frame buffer. So we will see more details about OpenGL as we see more examples of OpenGL during the course. OpenGL is also the interface between our application program and the graphics hardware. So it is a software interface to graphics hardware. The good things about OpenGL is that you have bindings for the OpenGL API in many languages. So in C++, in Java, in Python, in Rust, and so on. So it's cross-language. It is cross-platform. It runs on Linux, it runs on Mac, and it runs on Windows. And the API specification is open source. There is also an open source implementation of the API called MISA. And there is really, if you want all these features, there is no other alternative to OpenGL at that level of abstraction. An alternative to OpenGL that is platform specific is Direct3D. Direct3D almost has almost the same set of features as OpenGL has, but it runs only on Microsoft Windows. There are a few variants of OpenGL. So there is OpenGL ES, which is the embedded subset. So for handheld devices and embedded environments, you have a smaller subset of the OpenGL API. So this is what runs on almost all your smartphones and powers the graphics on your smartphones. Then there is WebGL. This is a JavaScript implementation of the ES API, and it runs entirely within your browser. So you can actually display very cool 3D graphics inside your browser, like without ever leaving your browser via WebGL. Now, over the years, OpenGL has evolved since it was introduced, and we will look at that evolution in the next lecture. But there is also thought in the graphics industry that perhaps to get more performance out of the GPU, we should be coding much closer to hardware. That gives the developer more control over how the hardware gets used to process the graphics API calls. So for OpenGL, many of these decisions are made by the OpenGL driver. So in response to this thought that has evolved in developers in the community, there have been alternatives to OpenGL and DirectX that have been introduced, which are much closer to hardware than OpenGL is. So Vulkan is a similarly cross-platform open source API that allows much more control over how the GPU works at scheduling your graphics calls and sort of allocating resources to your application program and so on. So while Vulkan is made by the same consortium that works on OpenGL, it's the Kronos consortium. There are other alternatives to Vulkan. There is Metal, which is very similar to Vulkan in spirit, but it is Apple only. So it runs only on Mac OS. and there is DirectX DXR, which is DirectX's evolution, just like Vulkan is OpenGL's evolution, closer to closer to hardware, I should say. So that is Microsoft Windows only equivalent of Vulkan. And what the development of all these things have allowed to happen is that they have pushed performance of graphics APIs to really, really new levels that allows them to do things like ray tracing now in real time. So for example, on this slide, you can see an image that has very nice illumination, lighting, reflection, and so on. This has been done using the Vulkan ray tracing API. Similar ray tracing APIs exist in DirectX DXR. These are more performant than OpenGL, but these are also much harder to teach. So we will not learn these things in the course. If you are ever interested in figuring these out, maybe we can talk about it in a project outside the course. Something that we will look at as a part of this course are shading languages. So OpenGL comes with its own shading language called GLSL, which is the OpenGL shading language. So what is a shading language? Your application code runs on the CPU, and it sort of compiles and links and then runs and executes code that directly runs on the GPU. So there is a part of your logic that exists in the application program, and there's a part of your logic that exists in the shader, and we will see which parts are these as we look at the implementations in detail. So the shader program is what runs directly on the GPU. And there are various languages for writing the shader program. So there is GLSL, the DirectX equivalent is called HLSL. Then there is CUDA. So CUDA is NVIDIA's homegrown shading language. And there is, these started off as, things for supporting accelerated 3D graphics. But then people figured out that the GPU was a huge multiprocessor, and it could do very efficient processing of large chunks of data in parallel. And so the GPU began to be used for more than just graphics processing, and this is known as GPGPU computation, so general purpose GPU computation. So CUDA has now evolved to become more than just a shading language used for computer graphics. It is also used for general purpose compute on the GPU. That is how all your machine learning libraries like TensorFlow and PyTorch are accelerated by the GPU by using the general purpose compute side of CUDA. So CUDA is of course proprietary. It belongs to NVIDIA. The open source specification that competes with CUDA is OpenGL. OpenGL is again made by the same consortium that makes OpenGL, and it's the open compute language. So just like OpenGL is sort of specialized for doing graphics, OpenGL is specialized for doing compute on a heterogeneous mix of compute devices. So OpenGL can run on the CPU and on the GPU. The same shader code can be executed. So these are specific languages, but there is also something known as the standard portable intermediate representation. So this is an intermediate language so that you can write device independent shaders. So you can actually write your shaders and compile them to the SPIR5 intermediate format. And then depending upon whether you are targeting your shader to DirectX or to OpenGL, you can then take that intermediate language code and target it to output GLSL or HLSL and so on. So it just makes writing device independent shaders easier. So we will not look at OpenGL and CUDA and HLSL and SPIR 5 in this course. We will only look at GLSL, but it will give you a fair idea of what you can do on the GPU. Now, as I said that OpenGL is this interface between your hardware and software. So let us look at slightly more detail, how your graphics application program talks to the hardware, and what are these different libraries that you are using in your code, right? So you are using OpenGL, and I talk about MESA sometimes, and I talk about GLFW, and so on. So what are these, and how do they talk to the hardware, that is your GPU? So you start by writing an application program, which in this diagram is, say, the 3D computer game. This game uses the OpenGL API in some high-level programming language. So say C++. So say this is your assignment code, which is your application program that is going to use the OpenGL API in C++, right? You're going to give as input to your code various kinds of data. It might be geometry data, it might be image data, or it might be sound data, and we are not really bothered about all the different kinds. We are primarily interested in whatever goes and results in graphics on the screen. But that is not the point. The point is that your application program can take various kinds of inputs, right? And then your application program needs to draw graphics to the screen, so it needs to open a window. Now, windowing on every OS is a platform-specific operation. So there exist libraries like GLFW or GLUT that allow you to access windowing functions and input devices like the keyboard and the mouse in a platform-independent manner. So GLFW is nothing but a wrapper API over platform-specific window managers. So on Linux, it interfaces with X Windows. On Microsoft Windows, it interfaces with the Microsoft Windows windowing functions. On Mac, it interfaces with the Mac OS windowing functions and their corresponding keyboard and mouse. The routines to handle inputs from the keyboards and the mouse in those OSs. Okay. So this is one side. So your application program A talks to a windowing library, and B, it also talks to OpenGL. So OpenGL now is so your application program made API calls. Now somebody needs to have the code for these API calls, right? So OpenGL might have a call like let us say GL draw element, and you might give it a list of triangles to draw. So that is just the API call. Where is the code for GL draw elements? So that code sits in the OpenGL library. So here in this particular diagram, the implementation of OpenGL is called MESA 3D, which is the open source implementation of MESA. This is present in Linux by default. However, if you install your NVIDIA or AMD drivers, you will have a proprietary implementation of OpenGL. Okay, and after this, your library, OpenGL library, will talk to a user space hardware specific DRM library, which is a direct rendering manager. So what is the job of the DRM library? It just takes the graphics calls and it schedules them, or it pipes them onto the kernel level components or the kernel level driver components, so the kernel level modules. So KMS and DRM are kernel space modules that talk to relevant hardware. So the kernel mode switch talks to your display controller and sets the modes of your screen or the monitor. So what are modes of a monitor? Say one mode might be, 1024 cross 768 at 60 hertz. So it's resolution 1024 cross 768 and it updates at 60 hertz. The screen refreshes 60 times a second. Another mode might be 1920 cross 1080 at 75 hertz. Okay, so there are different modes. So there needs to be something in the kernel that tells the screen, okay, now go to this mode. So KMS is what does that. And the DRM, of course, talks to the DRM in user space and pipes those graphics calls to the GPU and sends the relevant data to the graphics RAM or the GPU memory and so on. Okay, so this is the hierarchy through which your application program gets to talk to the hardware. Okay, now there is a slightly different view of the same. This has a little bit more detail, so you can see that you have the same. Oops, I'm sorry. You have the same. Let me get a pen. You have the same application program here. So this is like your application program, and the application program talks to your graphics library, and the application program also talks to your windowing, your window manager on your OS, which on Linux is the X server, and this happens via the GLFW library or the API in our case. So that is how the windowing works. The windowing itself might be accelerated. So to draw the window, the window boundary and the window header and the buttons and so on to the screen, X itself might talk to the OpenGL. So that is this interface. So you can see that so X and Wayland are just two different ways in which different ways in which you might have the windows and the input handled on X, let us say. So they both operate in a client server kind of a fashion, and they both might use accelerated rendering from OpenGL. So your application program is talking to OpenGL, X is also talking to OpenGL, and your application program talks to X via something like GLFW. That arrow is not drawn here. And then again, when you talk to OpenGL via the OpenGL API or OpenGL ES, let us say, then these will go via a DRM library. Like, so this is the DRM library. So you can see that if you have MESA, then your DRM library will be any one of these depending upon what you are running. So if it's an Intel chipset, you will have a DRM Intel. If it's an AMD chipset and you are running MESA, you will have DRM Radeon. If it's an NVIDIA and you do not install the NVIDIA proprietary drivers and try and use MESA, the DRM library will be DRM Nuvo and so on. And this is the user space DRM library that talks to the kernel space DRM library here via system calls. Whereas the kernel mode switch actually directly talks to X Windows. So X Windows tells it what kernel mode setting. I was saying switch. I'm sorry. It's kernel mode setting. So X Windows or the X server actually tells the KMS module what screen resolution and refresh rates to set. And then these actually directly talk to the hardware. Okay, so if you can see that if you have MESA, then you go through these and you go through these and they talk to the GPU. Whereas if you have implementation from NVIDIA or from AMD, that these are the proprietary ones. So FGLRX is AMD's proprietary driver. If you have the proprietary drivers installed, then everything is just a big binary blob. You do not know what these guys are doing inside, and this blob just copies as a kernel module on your in your installation, and that talks to the GPU. Okay. So the internal details of this blob are not known, whereas for the open source case, the internal details are known. So this is just another view into the same hardware software interface that happens when your application program talks to the graphics hardware. So I'm just showing you both of them because both of them have slightly different detail, and hopefully if you look at these and you ponder long enough, you will get an idea of how your application program is talking to the GPU. Of course, you can go to say this link and this link here and read up more about how these things happen. Okay, if you are interested. So the only library that I haven't talked about that we will use is GLEW. So what is GLEW? So OpenGL is this API, and to introduce features into OpenGL, there is this huge consortium that meets once in a while and decides how you should extend the OpenGL API, or how the OpenGL API should evolve across versions, so from say 3.3 to 4.1 to 4.6 and so on. But that takes a lot of time. And in the meantime, hardware manufacturers might want to introduce experimental features because, so for example, say AMD has made this cool new graphics card, and they know that it is capable of doing something, and they want to expose that capability to OpenGL. So they can do that by providing a specific extension to OpenGL that will only be available to OpenGL on the AMD card. Okay. So these specific extensions are available to OpenGL depending upon what hardware you are running, and they are not pre-known, so they cannot be preloaded. They have to be dynamically loaded at runtime. So the code to do this dynamic loading is a bit verbose, and it is difficult to write again and again. So GLEW is the short form for the GL Extension Wrangler. It is a library that helps to figure out what extensions are available to the OpenGL implementation that is present in the system, and it helps you to load these extensions easily. We will not actually use any extensions because there is a lot of heterogeneity in the hardware that we are using. So we will not depend upon any extensions. We are only using GLEW to test what version and profile of OpenGL the system has. Okay, so you will see that we ask for a particular OpenGL major version, a particular OpenGL minor version, and whether shader-based OpenGL is available on the system or not. So we are only using very minimal capabilities of GLEW, and that too in the very initial bootstrap part of the code, and then we don't use GLEW at all. So there are like a handful of GLEW calls, and then GLEW is not used. After that, we use GLFW to handle everything that relates to the window, and that relates to the keyboard, and that relates to the mouse. And other than that, we only use OpenGL and GLSL. We will use a helper library called GLM, which is just a header library for making, which has additional math routines for making our lives easier when we write GLSL code. So we will see, so GLM is short form for GL Mathematics or GL Math Library, and we will see how GLM gets used. So it has various helper classes like, like 3 vectors and 4 vectors and 4x4 matrices and so on and so forth. So we will see what GLM is when we get to actual code, but that is the spectrum of libraries we use. And I hope that by now you have a fair idea of what OpenGL is all about. And in say 1 or 2 more lectures, we will see OpenGL application code in much more greater detail. So thank you.